Okay, so today we're basically just going to go over a bunch of basic definitions. It's not, not the most exciting thing, but these are just like the basic language and basic language of points at topology, and it's something that everybody, basically all mathematicians know. So you have to know this stuff. It's like just fundamental knowledge. So I'm going to back up a little bit because just to remind us what we're doing. So basic definitions. So we're in a metric space, right? So there's some space and it has a metric on it, right? And then we have this thing called a neighborhood, right? Neighborhood is sort of a generalization of a ball in Rn, right? Ball in Rn, of course, you have a center, and then you have everything within a certain radius, right? And that's exactly what we do with a neighborhood, right? So you have some point in the space, and you have some real number. You have some radius, and then we have this thing nRP, which we define to be everything in the space, right? So all points in the space that are within that radius of the center, right? So same sort of idea, right? So okay, so yeah, so like in the normal, if I define distance in R2 in the normal sense, right? Distance between 2 points as being just the magnitude of the difference when b, x1 minus y1 squared plus x2 minus y2 squared, right? Then that would look like this, right? If I were talking about a ball, a neighborhood of radius r about the origin, right? That would look something like this, right? Right. Just for amusement, what if I define distance as x1 minus y1 plus x2 minus y2? So you have 2 points. The distance is defined as this plus this, right? Right. So if this is point x and this is point y, the distance is this. In that case, what would be the unit ball around the origin? What would be the unit neighborhood around the origin? What would that look like? Right. What is distance? What are all the points that are distance 1? Here's the origin, right? Here's the origin right here. What points would be distance 1 from the origin? Can you name any points that would be distance 1 from the origin? Just like shout out some points.
1, 0.
1, 0, yeah, sure. 1, 0, that'd definitely be distance 1 from the origin. This would be 0, 1, negative 1, 0, right? These guys are definitely distance 1 from the origin. Anybody else? Any other points? Any other sort of obvious points? Madeline, you're smiling?
Be like the square root of 2 over 2.
Square root of 2 over 2.
Like square root of 2.
Would that be distance 1 from the origin? That would be.
We defined by that way.
Yeah. So we're using this distance, right?
Then it'd be like 1/2.
1/2, 1/2. Yeah. 1/2, 1/2. That would be distance 1 from the origin, right? 1/2, 1/2, right? And like 3/4, 1/4, right? 1/4, 3/4. So you see that in this using this metric, the unit ball around the origin is this diamond shape, right? Okay, just very amusement. Okay, so that's generalization of a ball, right? We define this thing, which is the everything whose distance is less than r but bigger than 0, right? So we don't include the center point in this case, right? This is what I call the punctured neighborhood. Okay, right? So we don't allow the distance to be 0. We exclude the central point. Okay. And then we have this definition of limit point, right? So you have a subset in X, and you have a point in X, and we say that P is a limit point of E if something happens. Does anybody remember what that is? What's the limit point, Charlotte? Yeah.
It's if there's some Q such that Q does not equal P and Q is an element of E.
Okay, so if there exists a point, if there exists a point Q in the space, maybe? So
Yeah.
such that, say it again?
That Q does not equal P.
Q is not equal to P, and
Q is in E.
Q is in E. Okay, so not quite. So all that would mean is that, so here is E, and then let's suppose this is P, okay? There exists a point Q in X, there exists a point Q in E that's not equal to P, okay? That would mean, okay, here's Q, and it's in E, and it's not equal to P. That would mean that, so P is the limit point in this picture, right? But in that case, is this a limit point? Basically everything would be a limit point, right? Anything that's not equal to Q would be a limit point in this case. So not quite. Anybody? The picture you want to keep in your mind is like this. P is so close to Q. P being a limit point of E means sort of like it's close to E, right? So close that no matter what neighborhood you take, there's always somebody from E inside that neighborhood. Okay, that's kind of the picture. So maybe that's what you're going to say, Anne. Sorry. Yeah. So okay. So this wouldn't work out. This would not be a limit point because I can find a neighborhood that's got nobody from E inside there. Okay, right. So so the condition's like this. P is a limit point of E if no matter what neighborhood you're given, so no matter, right, so for all neighborhoods, the punctured neighborhood of P intersect E is not empty. Okay. In English, every punctured neighborhood of P intersects E. Okay. Yeah. Yeah. So yeah, it takes some getting used to the conditions. So don't worry. Just make your mistakes and keep on going. You in this game, you don't want to be too cautious. You just want to be like, is it this? And the answer is no, and then you're like, okay, then I'm correcting my idea, right? That's you want to. So I think I've said this in other classes. When I was learning Chinese in college, my professor said, the key to learning is shamelessness. And that's when a kid is learning a language, they just say whatever they want, and then the parents say, no, that's not right. My daughter, when she was little, she thought her name was you, because we'd say like, can you do it? Can you do it? So she'd say, let you do it. Let you do it. If she wanted to do something, right? And eventually, she figured out that you was not a name, but a pronoun. is that right? A pronoun, yeah. Yeah. Anyway, so yeah, the key to learning is shamelessness. So, P is the limit point of E if no matter what neighborhood you take, right? So for all neighborhoods, for all radii, every punctured neighborhood intersects C, right? So kind of the standard picture is you have, let's say that we're in R1 and we have 0, 1, right? Then what are limit points here? Well, if I'm here, if I'm here, then maybe some neighborhoods will some punctured neighborhoods will intersect, but not all of them, right? I can find a punctured neighborhood that doesn't intersect my E, right? So this is not a limit point, right? What about if I'm inside the set? Is that a limit point? Check. Does every punctured neighborhood intersect the set? Sure, right? No matter what punctured neighborhood I take, right? No matter what punctured neighborhood of that point I take, right? There's always some points that are common to that punctured neighborhood and 0, 1, right? What about if I'm at 1? Is that a limit point? The answer is yes, it is. Yes, it is because here's 0, 1. I'm looking at this point here, right? It itself is not in the set, but that doesn't matter, right? The point 1, all you care about is look at punctured neighborhoods, right? So look at punctured neighborhoods. Do they intersect? Do they intersect 0, 1? Sure they do. Like no matter what I take, they're always going to intersect that interval of 0, 1. Okay. Okay. So that's the notion of limit point, and it's very important. Okay. Right. These first two notions, neighborhood and limit point, are really crucial. Okay. Definition 3. If E contains all its limit points, we say it's closed. E is closed, or E is a closed set. Okay. So just now, for example, the interval 0, 1 is not a closed set because 1 was a limit point, right? And 1 isn't contained in there, right? What about the closed interval 0, 1? Well, it's kind of given away by the name. Yes, it is closed, right? The limit points of this, right? Right. The things that are not limit points are the things outside of the set, right? Everything in the set are the things that are in the set are its limit points, and it doesn't have any other limit points, right? Right. This is okay. So yeah, closed. Okay. Okay. Definition 4. If P is in the set, but not a limit point of E, then we call P an isolated point. An isolated point of E. Okay. So if you're not a limit point, what does that mean? So logic question. You are a limit point means that every punctured neighborhood intersects E. If you're not a limit point, means what? Anne?
Some neighborhood doesn't intersect E.
That's right. Some punctured neighborhood doesn't intersect E, right? So, the picture is, so it's equivalently, right? If there exists some neighborhood such that that neighborhood of P intersect E is empty. Right? So there's some punctured neighborhood that doesn't intersect E. So your point is in E, right? P is in E, but there's some neighborhood around it where everything, there's some neighborhood around it where all the points except for P are not in E, right? So everything in here is not in E, right? Except for P itself, right? So P is in the neighborhood, and there's P is in E, and this whole there's a set around it that's not in E. Okay, so it's isolated, right? Makes sense, right? Right. This point P is part of E, but he has no friends. There are no friends from E inside there. Okay, it's isolated. That's me in high school at lunchtime. I'm not sure why, but yeah. Anyway, yes.
Oh, I was just gonna ask, if you had like a segment that was like 0 to infinity.
Yes.
Is that closed, or is that?
What kind of a segment? A segment.
Like, or closed, like including 0, or like including some number to infinity?
Okay, you tell me. You tell me. Does this contain all its limit points?
No.
No. Does this contain all its limit points?
I think yes.
What limit point does it not have?
Let's see.
Can you find a point that is a limit point can you find a point that's a limit point of this thing that's not in this thing?
Like what, infinity?
Infinity is not a
Okay.
not a number.
Um,
Yeah, not a point, right? What's the distance to infinity? Right. We don't count. Infinity is not a real number.
Okay.
Yeah.
Okay, so then that would be a closed.
Yes, this is open and this is closed. Yeah.
Thank you.
Mhm. Yeah. Sure. Okay, isolated point. Yeah. Okay. Yeah, I don't mean to say that I was a lonely person in high school, by the way, but rather just that for some reason when I ate lunch, I was always solitary. Okay, I think I'm getting sort of distorted picture here. Anyway, yeah, what's next? Yeah, so next is the idea of interior point. So this is all basically talking about closed sets. Important idea of closed set. Isolated point, not that important. Closed, the big ones here are circled. Okay, interior point, right? So you have a set, you have a point, you have a point inside the set, and if there exists a neighborhood such that the neighborhood of that point is contained in the set, then we call P interior. Right? We call P an interior point of E. Okay, an interior point of E. So what that means is that you have some set, say here's E, and you have some point, and you can find there exists a neighborhood that's entirely contained inside of E. Okay, there exists a neighborhood that's contained inside of E. It doesn't mean that all neighborhoods are contained inside of E. You don't have to. That would be too crazy, right? That you don't have to have all neighborhoods, but there must be one neighborhood that's contained inside of E. Okay. So, for example, is 0, 1? Is this point interior? Sure, right? Because I can just take the minimum of the distances to here and here, and I use that as my radius. Right? I use that as my radius. I get a neighborhood that's contained inside of 0, 1. Right? So, right, here's this point, right? And I would look at a neighborhood where the radius is the minimum of the distances between 0 and P, and between 1 and P. And that would be contained inside of 0, 1. Right? Just to show you how one might rate that. Right? The minimum of the distances to the endpoints, use that as your radius. That radius gives you something contained in the set. Okay. 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 Next, 7. If E consists only of interior points, then we call E an open set. E is an open set. So if every point is interior, then we say it's open. Okay. Right. Is this an open set? No, right? Because these boundary points are not interior, right? You can't find an interval, no matter how much you try. You can't find a neighborhood of this point that's contained inside the set. Right? What about the entire real line? Is that an open set? Yes, yes it is, right? Because every point you can find a ball, you can find a neighborhood around it that's contained in the set. Right? Is the real line a closed set? Does it contain all its limit points? Well, it's the whole space, right? It's the whole space, right? So, yeah, it is also a closed set. So it's closed and it's open. Okay. We call such sets cloped. No, nobody uses that term. Okay. No, don't say that. Don't ever say that. It is a term, but I've never heard anybody serious use this term, cloped. You say both open and closed. Yes, that's what you would say. Okay. Okay. Very, very important idea. Open sets. Okay. So, other kind of less consequential ideas. Well, at least for now. Oh, I mean, okay. I don't think these are, in my mind, less important. They're less subtle. Okay. So, if you have E, then you have E complement. You guys know what E complement is, right? It just means everything that's not in E, everything in the set that X is not in E, right? Complement. E complement. Right. Okay, I don't even want to do this one, but if E is closed, and every point is a limit point, then it's called perfect. Not that useful a term, but it's defined here. More important, if you have a set and if there exists a neighborhood, NRQ, say, that contains your set, then we say E is bounded. Bounded, right? So it just means contained in some ball. Okay, so like the real line, not bounded, right? There is no finite ball that's going to contain the real line, right? If I look at some interval, bounded, right? Because I can find a ball that contains it, right? I can find the ball that contains it, right? So bounded. Okay. Also important, if every point of X is, so again, E is a subset of X. If every point of X is either in E or a limit point of E, then we say E is dense. Dense in X. Dense in X. So for example, the rationals are dense in the reals. The rationals are dense in the reals because every real number is either a rational number or it's a limit point of the rational numbers. Does that make sense? Right? If you have the real numbers, you have the real numbers, right? The rationals live inside them, right? The ones with denominator 1, the ones with a denominator 2, the ones with a denominator 3, et cetera, the ones with a denominator 4, et cetera, right? So the rationals live inside, right? And every point in R is either a rational number or it's a limit point of the rational numbers, right? Because if I take a non-rational number, say the square root of 2 here, right? Every neighborhood is going to contain rational numbers, right? That is the Archimedean, no, that is the density property that we proved right after the Archimedean property, right? So yeah. Okay. So the rationals are dense in the reals. Okay. Okay. Everybody okay? Okay. So the basic definitions, and we're going to spend some time proving like how these things relate to each other. Just basic facts of how these ideas are connected to each other. Okay. So so the first thing we're going to do is prove the following, that every neighborhood is open. Okay. Every neighborhood is open. Okay. So, right. So we have some metric space. Right. Our setting is that we have some metric space, and we have some neighborhood. A neighborhood inside in X, right? And we want to show that it's open, right? So we want to show that this thing is open. Okay, so let's just translate. What does that mean? What does it mean to show that this thing is open? We need to show that
every point is an interior point.
Right. In other words, every point is interior. In other words, right, so every Q in the neighborhood is interior. In other words, what does that mean to be interior? That given the point, you can find a neighborhood around that point that's contained in this thing here, right? Given any Q in the neighborhood, can find a radius, let's call it, I don't know, S, such that the neighborhood radius S around Q is contained in the other neighborhood, in the bigger neighborhood, right? Right. So the picture, right? You can imagine that we're in R2, right? Somebody gives us a neighborhood, right? So here's a point P, here's a radius R, and says, show me that every point inside here is interior, right? So okay, pick some arbitrary point Q. We want to show that there's a radius that's small enough that fits inside here. Okay. So what radius should we choose? What do we take as our radius? Right. We want to show that given any Q, we can find a radius S so that neighborhood is contained in the original neighborhood. Right? So what do we take? Right? The game is, what radius do we want? Okay, so talk to each other for a minute. I'll walk outside in the rain.
I mean, probably just like the smallest one you can, so you know that it's contained, but,
I was thinking it would just be like anything less than
oh, yeah.
whatever. We're talking about the distance between P and Q?
Well, I think because like it's already in the neighborhood, right? So we're just trying to find the radius for Q.
Okay, what are we going to take as our radius? Any ideas? N.
I said anything less than R.
Anything less than r. So suppose I'm here at this point here, and I take 0.9 r. Okay, I take this distance, right? That means I would take like this distance as my r, as my new radius. Is that going to work?
Like the difference between R, those two?
The difference between r and
I don't know how to say it, and the radius. And the difference between R and the distance between P and Q.
exactly. Yeah, you got it. So look at this distance here and subtract that from this distance, right? That'll give you, so we're here like this, right? We have some radius, we have some point, so this is P, this is Q, right? This distance is R, right? And so what we take is, we'll take this distance, right? We'll take the distance to the boundary, basically, right? We'll take the distance to the boundary, right, and use that, and that will keep us inside, right? Or we could take, if we want to be really careful, cautious, we'd take maybe half the distance to the boundary. Distance to the boundary works fine. So yeah, so let the idea, let S be the difference between R and the distance from P to Q. Okay, so now we're claiming that this thing is contained inside of this thing. Okay, so we do have to prove that. Like the picture seems like it's right, but let's make sure that we can actually write this down, right? Claim that this thing actually is inside there. So in other words, we have to show that if we pick any point inside here, it's still inside the original neighborhood, right? So again, make it clear. And one thing that I found really useful when I first started doing proofs is making clear what you wanted to show. Right, so I would always start my proofs. We want to show that this is contained in here. In other words, given any point x in here, x is also, we have x in here. Right. In other words, we want to show that if the distance from x to q is less than s, then the distance from x to p must be less than r. Right? Okay. Right. So is that true? If the distance from x to q is my x, if my distance from x to q is less than s, right? And remember, s is this, r minus the distance from P to Q, then the distance from x to P must be smaller than r. Okay? Okay. Here's the distance from x to P. How do we know that that's smaller than r? We know we have a control on the distance from x to Q, right? We want to get a control on the distance from x to P. How can we do that? Can we control the distance from x to P with something else? Yes?
Triangle inequality.
Triangle inequality, right? Triangle inequality says the distance from x to p is controlled by the distance from p to q plus the distance from q to x, right? Right? X to p is controlled by x to q, q to p, right? Well, the distance from q to x, right, is controlled, this thing is controlled by r minus the distance from p to q, right? So we get the distance from x to p is controlled by the distance from p to q plus r minus the distance from p to q. In other words, it's controlled by r, right? Actually, we can make this strict because this one was strict. Okay, this was less than or equal to this, but this guy is strictly less than this. So now this guy is, right, strictly less than their sum. Okay, right? In which that's what we wanted, right? The distance from x to p is strictly less than r. In other words, the point is in the set, in the neighborhood. Okay. Okay. Everybody comfortable? Okay. 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 So yeah. So every neighborhood is open, but I mean this is mainly to give you some sense of like how to do proofs, how to do this sort of topological proof. Okay. Another one. Okay. So if P is a limit point, let me introduce some notation. So if E is a set, we're going to let E prime denote the limit points of E. Okay. So that's introduced a bit later, but let's just introduce it now. So if P is a limit point of E, then every neighborhood of P contains infinitely many points, infinitely many elements of E. Okay. Okay. So remember what a limit point is, right? Limit point means that every punctured neighborhood contains an element of E, right? So here's P here. Every punctured neighborhood, right? Every punctured neighborhood of P, will intersect E, right? But what this is saying is that if you're a limit point, in fact, every neighborhood contains infinitely many elements of E. Right? And maybe that makes sense, right? Here's the idea, here's the picture. So here's the picture. Why is that pretty straightforward? Suppose this guy is a limit point, right? That means that no matter what punctured neighborhood you take, there's somebody from E inside there, right? So then use that as your new radius. This punctured neighborhood must contain some element of E. There must be some element of E inside there. Use that as your new radius, right? And so on and so forth. So you just keep on going, right? Use that as your new radius. Every punctured neighborhood must contain some element of E. It's not E2 because that's not in the set, right? So there must be an E3 inside there, and so on and so forth. Okay. I don't know if I want to write this out. That's basically the idea. Right, so roughly proof. So proof. Take any neighborhood of P, right? Then, so since P is the limit point, we know that NR star P intersect P contains some E1 in E. Right. The punctured punctured neighborhood intersect E contains some element of E, right? Is non-empty. Is non-empty. In other words, contains some point that is in E. Right. So now let R2 be the distance from P to E1. Right. Let R2 be the distance from E to P1, from P to E1. Then and R2 punctured P intersect E contains some E2, right? Contains a point E2 that's in E, and E2 is not equal to E1, right? And then continue. Okay, so I'm not gonna, you can do it by induction, basically. Okay. Okay. So that's kind of a useful theorem. Here's another one that's important. So E is open if and only if E complement is closed. E is open if and only if E complement is closed. Okay, so that's in some books that's actually how they define closed sets. They say, we define a set to be closed if its complement is open. Here we've gone the other way, and we've said a set is closed if it contains all its limit points, and now we're going to see that these things are that this complement way also works. Okay, so so let's prove the forward direction first. Suppose that E is open. Okay, and let what do I call it? X. Let X be a limit point of E complement. Okay, X is a limit point of E complement. I would write X is in E complement limits, but that seems too much notation. Okay, so let X be a limit point of E complement. So what does that mean? That means that here's X, and that no matter what neighborhood you take, there's somebody from E complement in there, right? So there's somebody from E complement in there, right? So no matter what neighborhood you take, there's somebody from E complement in there, okay? So what does that tell you? So in every neighborhood of X, there's a point from E complement. Okay, but in that case, X is not an interior point of E. Right? X can't be an interior point of E, right? Because to be an interior point means that you can find a neighborhood that's contained entirely inside of E, right? But for us, no matter what neighborhood you take, there's somebody from E complement in there, right? So you can't find a neighborhood that's contained entirely in E, right? So X is not an interior point of E, right? But E is open, which means that all of its points are interior points of E, right? So that tells you that X cannot be in E because E consists, right, of interior points. Consists only of interior points. Okay. Maybe I'll introduce another notation. People use this to denote the interior, the set of interior points of E. So to be open means that you are equal to all your interior points, right? And what we're saying here is X is not an interior point of E, so it's not in E. Is this okay? Okay, yeah, so a lot of vocabulary. Okay, a lot of vocabulary, but you'll get it eventually. Somewhere near the end of my education, a friend of mine said, I wish they had told us that everything was trivial. Everything we were going to learn was trivial. In some sense, that's how you want to think about. I don't know if that was true of our entire education, but this part of the education, you're going to look back and say, wow, this is just like 1 + 1 kind of stuff. Okay. So yeah, don't be intimidated by just the masses of words. It's just words, and you just learn the definition of the words. Okay. Okay, this is probably the last one we're going to do today. So going backwards, suppose that E complement is closed. Right? Suppose E complement is closed. Right? We want to show that E is open. Okay. So so let X be a point in E, right? Okay. We want to show that X is actually an interior point of E. Okay. So X being in E means that X is not in E complement, right? X being in E is the same thing as saying X is not in E complement, right? But E complement is closed, right? Since E complement is closed, right? It contains all its limit points, right? So it contains all its limit points, so that means that X can't be a limit point of E complement, right? X is not a limit point of E complement, right? Because E complement contains all its limit points. Okay, so X is not a limit point of E complement. And remember what that meant? That meant that you can find a punctured neighborhood that doesn't intersect E complement, right? That's what you said, right? So there exists a punctured neighborhood around X that doesn't intersect E complement. There's a punctured neighborhood around X. There's a punctured neighborhood around X that does not intersect E complement. So E complement is outside here, right? There's nothing from E complement inside here, right? But X is in E, right? So what does that mean? That means that everything in this punctured neighborhood is in E. Right? So everything in the punctured neighborhood is contained in E, right? Because it doesn't intersect E complement, right? Everything in the punctured neighborhood is in E, and also the center is in E, right? So I can say the whole neighborhood is contained in E, not just the punctured neighborhood, but the entire neighborhood. The punctured neighborhood plus its center, that is the entire neighborhood, is contained in E, right? And so we found, so what does that mean? That means that X is interior to E, right? Because we found the neighborhood around X that's contained entirely in E. So, okay. So X being in E, we wanted to show that X was in the interior, and indeed that's what happens. X is in the interior. Okay. So next time we'll do a little bit more of this stuff, and then we'll get on to the super important idea of compact sets. Okay, so yeah, that's one of the big ideas of this course. The notion of compact set is the answer to like a lot of the mysteries in calculus.